In this lesson, we're going to be talking about the chi-squared goodness of fit test. Now we use the chi-squared goodness of fit test to determine how well a set of observed sample values match those expected from a hypothesized population distribution. Generally, the hypotheses are, for the null hypothesis, that the sample data is distributed in a certain way, and for the alternative hypothesis, that the sample data is not distributed in a certain way. Now for the number of degrees of freedom, nu, we find them by nu is equal to n minus 1, where n is the number of classes. However, if a certain population parameter is unknown and has to be estimated from given data, then the degrees of freedom nu will be n minus 2, where again n is the number of classes. Now, as we are getting into carrying out a goodness of fit test, you need to remember what we said in the previous video, that the test statistic x squared is found by the sum of O minus E squared over E. And you also need to note the rule that expected frequencies must be at least 5, so E must be greater than or equal to 5. And one more thing, you need to understand that chi-squared tests are always carried out in the upper tail. Right, so right now we want to look at a question from a past paper and see how we can carry out a chi-squared goodness of fit test. So here's the question. Alright, so let's work on it. The question says, a random sample of 50 observations of the continuous random variable x was taken, and the values are summarized in the following table. So we have this table here with observed frequencies. It is required to test the goodness of fit of the distribution with probability density function f given by f of x is equal to 3 over 16 of 4 minus x to the power of a half for values of x ranging between 0 and 4 and 0 otherwise. The relevant expected frequencies, correct to 2 decimal places, are given in the following table. So we have this other table here with expected frequencies. So on part 1, they say show how the expected frequency for 1.6 to 2.4 is obtained. Alright, so here they are asking for this particular expected frequency, which is 10.59, and they're asking how it was obtained. Now, expected frequencies are calculated from the distribution. In this case, we have a continuous distribution f, from which the probabilities are being calculated, as well as the expected frequencies are being derived. So here, using this function, I'm going to calculate the probability that x would lie between 1.6 and 2.4. And I do that by integrating within the limits 1.6 to 2.4, the function 3 over 16 of 4 minus x to the power of a half, and that's with respect to x. So let's do that. So here we are factoring out 3 over 16, and inside the bracket I'm having the integral of 4 minus x to the power of a half, which we get by 4 minus x to the power of a half plus 1, which is 3 over 2, and that's over minus of 3 over 2. And the limits we have 1.6 to 2.4. Alright, so let's simplify this. Here we have the 3 over 16, and here we have minus 3 over 2 at the bottom, which is as good as we have, factoring it out, times minus of 2/3. And inside the square bracket, we have 4 minus x to the power of 3 over 2, like this, and the limits 1.6 to 2.4. Alright, so let's now substitute. That'll be here 3 cancels out with the 3, and 2 gets into 16 8 times. So we'll be having here left with 1 over 8. And inside the bracket, substituting 2.4 for x, we'll be having 4 minus 2.4, which is 1.6, and that's raised to the power of 3 over 2. And that's minus 4 minus the lower limit here, 1.6, and we get 2.4, so that's 2.4 raised to the power of 3 over 2. Alright, so we can make use of the calculator for this. So that's minus of an eighth, and that's of 1.6 raised to the power of 3 over 2, which is 1.5, and that's going to be minus 2.4 raised to the power of 1.5, and this is going to give us 0.2117 going. So 0.2117 and going. So this is what we're getting for the probability. Now to get the expected frequency, since we have a sample of size 50 as given, then we are going to say for the expected frequency, that's going to be 0.2117 that we got multiplied by 50. And here it's times 50. And this gives us two decimal places, 10.59. So we have 10.59, which is actually what they have here as the expected frequency. So I'll say here shown. So that's how we do it with this particular one. Let's go on to the next part. On part 2, the question says, carry out a goodness of fit test at the 5% significance level. Now you need to understand that a goodness of fit test, we use it to see if the distribution, which in this case is the distribution F, fits the data given. So this is data obtained from an experiment, and we want to see if these two will match. Alright, so for the null hypothesis here, that's H0, it'll be that the distribution F fits the data given. And therefore, for the alternative hypothesis, it'll be that the distribution F does not fit the data given. So these are the hypotheses. Now next, we'll need to calculate the test statistic. Now the test statistic, that's x squared, is calculated by the sum of or minus e squared, and that's over e. So here, I'm gonna put down the observed frequencies against the expected frequencies. Now from the information given, the observed frequencies, we have 18 corresponding to 14.22 on the expected frequencies. We have 16 corresponding to 12.54 on the expected frequencies. We have 8 corresponding to 10.59 on the expected frequencies. Now you need to remember that the expected frequencies should always be greater than or equal to 5. And if you look at this value for the expected frequency, you can notice that it is actually less than 5. So what we do here is we are going to combine this to the adjacent one, so that we'll be having, adding the two, 12.65. And we'll also be adding the observed frequencies, so adding this two, we'll be getting 8. So this is how we do it when we have expected frequencies that are less than 5. We combine them with adjacent expected frequencies. Alright, so we now have this information here from which we can now calculate the test statistic x squared. So we'll be saying here for x squared, that will be 18 minus 14.22 squared, and that's over 14.22, and that's plus, here we'll be having 16 minus 12.54 squared, and that's over 12.54, and that's plus, for the next one here, that will be 8 minus 10.59, and that's squared, and that's going to be over 10.59 here. And lastly, we will be having 8 minus 12.65, and that's squared, and that will be over 12.65. So we are adding these. Right, so let's do the working. So I'll have my calculator here, starting with the first one. That's 18 minus 14.22, and that's close squared, and that's over 14.22, and that's going to be plus, and we have 16, and that's minus 12.54, and that's close squared, and that's going to be over 12.54. Then next, we are going to have 8 minus 10.59, and that's close squared, and that's going to be over 10.59. Then lastly, we are going to be having 8 minus 12.65, and that's close, and that's squared, and that's going to be over 12.65. And this gives us 4.30 here. So we get 4.30 for the test statistic here. Right, so now that we have the test statistic, we will need to know the critical value, which is chi-squared. And for the degrees of freedom, since we have 4 classes, the degrees of freedom will be 4 minus 1. So we'll be having 3 degrees of freedom. And since it's a 5% significance level, the p-value is 0.95. So if we go to the tables, we will see that 3 degrees of freedom and 0.95 corresponds to 7.815. So we have 7.815 for the test statistic. And I think you can notice from the graph that the test statistic here is actually less than 7.815, which is the critical value, which means that it lies in the acceptance region where we do not have evidence to reject the null hypothesis. In other words, we are accepting the null hypothesis, which says that the distribution F fits the data given. So for the conclusion, I'll say that the distribution F fits the data given. And that's how we do it.